All right. So yeah, so I did a little bit something extra without streaming earlier yesterday. Basically, I wanted to start to figure out how to actually use the RAM uh, regions of the FPGA that are available. And the thing about the RAM is there are a couple ways that you can use the RAMs. So every FPGA these days includes something called block RAM. So areas on the fabric of the FPGA which can actually be built into whatever type of memory you need. Custom address size, custom data size, single port or dual port. Dual port is something you don't really find in implemented RAM modules, right? Because dual port means that you can actually have two different circuits that are reading and or writing to the RAM at the same time. It's not really how regular RAM works, right? Where those requests have to be synchronous, so only one can happen at a time. We don't need to do any of that fancy stuff, at least not yet. But I built out a RAM. I'll show you how that worked. But basically, to try and start to get the RAM to work, the first thing I thought I would do is just to have the RAM be used for the color data, which is quite fun. And by accident, basically, that color data ended up giving us this really interesting aesthetic, kind of this like cyberpunk kind of look to it. I don't know, Blade Runner-ish or something, kind of retro future blue to red thing happening with the background here. But anyway, so I'll show you what's going on here. So this up a little bit. All right. Yeah, okay, that'll work. All right. So inside our display, inside our graphics compositor, where'd it go? Inside our graphics compositor, we instantiate a new component of a type called simple RAM. And I made it. There it is. No. And now I cannot. I don't see it in my project hierarchy. There it is. All right. Fine. Okay. So simple RAM. There are ways you can do this differently, right? You go into IP Integrator, you can create a whole block design, and then you can add components from the catalog, and it's a whole thing, right? If I come into the IP catalog here, you'll see RAM. So you can add all kinds of block RAMs, and you can drag and drop these components, and you can see what they look like, and it's a whole thing, and that's a very Xilinx way of doing it, but what you lose is portability. So instead, you can do something called inferring RAM. So basically, if you write the logic here that basically describes the function of RAM, right? So RAM, you'd be able to read it, you can write it, you have to give it an address that you want to read from, or you have to give it an address you want to write to, as well as the data you want to write to that address. And it has to be tied to a clock, so you have to take a clock in, and it has to have a certain size, so those an address width, maybe there's a total number of elements that you're going to support, and then you have your register array of data that you want to store. And then you have the simple clock functionality, right? To say, okay, well, whenever the clock is at the positive edge, right, whatever is, collect the address register so that you can read data from it. And by the way, if if you actually have a write enable signal, then we're going to set that memory address to the data that we're receiving as an input. And no matter what, every clock cycle, we're also just constantly making sure that our data out is equal to memory that's at that address register, which gets set here. So pretty straightforward, very, very simple, but really essentially defining what a RAM is. And when you define a file, a component like this, and you actually instantiate it, which I use, instantiate it over here. I connect a bunch of different lines to it. Then what happens is you'll see here in the design run, when it's doing the synthesis, it says, okay, well, I need a bunch of lookup tables for some of the logic. I need some flip-flops for my logic, and I'm going to use some block RAM. And there you go. So it's actually using the block RAM in its implementation. So I haven't done this before, but if you look at the synthesized design, I think it's over here. Let's check. So this is a clock unit. Okay, yep, that we're using to do our DVI timings for HDMI output. These guys are our memories. You can see here RAM blocks being used throughout our system. Each one over here, you can see their names over here. All this memory getting used now. So anyway, what's nice about that is, again, super flexible. We can make it do whatever we want within some limits. So for example, over here, I've set it up to be a 15-bit address bus, storing a total of 32,768 bytes. So we're actually addressing individual bytes in memory. It's not a 32-bit thing. It's not a 64-bit thing. I wanted 8-bit, and maybe later we can make it, more capable. And so I was at the point where I was able to build in this memory, but I wanted to put some data into it. And it turns out there are a couple ways to do it, but the simplest way I thought was you can actually have it set up so that during synthesis it's going to read a file and then put that data into memory. So that as the FPGA starts up with your design, it will actually have data in memory already. And that's just a clever shortcut for now. I mean, eventually I'd like this to be loaded in dynamically from a program, loaded from a CPU that's on the same board as the FPGA, but you have to go one step at a time. So it seemed like a good way to start. So, so you can see here right now, this data is being read in from this file, ramdata.bin, and it gets read in over here and gets stored into our memory array, right, which we have, defined up here, which actually stores all the data for the memory and, then gets used for the RAM. So what's in ramdata.bin? This is where I was starting to play around with the colors over here. So it's a pretty simple file. The way that these get defined to be used is every line represents one address. So you can see I have 32,768 addresses. And some of it is just, it's a repetitive sequence, but basically all that this is a sequence that starts at 0 and it counts up to 255. So if we go to line 255, you'll see line 256. Line 256 is all ones, and then flips right back down to 0. So So the RAM is very, very simple. It's literally just a repeating sequence of 256 values. And so then I wanted something to be able to do with those values and something easy to start. So all I did for now is I took our background compositor, I hooked it into the RAM, and in our background compositor, which remember shows the shows our Goomba pattern there, I said, instead of using these color palette colors that we used from before with the Goombas, we pretty much kept those the same, but I replaced the red color that was defined from the palette to say actually the red color is always going to be just defined by the whatever value is in our RAM at the address that is equal to the first 15 bits of the X coordinate. So as the system scans, left to right, it's in here, and it's going to look from left to right on every row of the pixels, and the X value is going to keep increasing as it goes to the right. We're only going to capture the first 15 bits of it because we only have a 15-bit memory, so there's no value. The X coordinate here is actually a 16-bit number, but our memory isn't that big. And this was just a little hack to make sure that this works. So it looks at the X coordinate, it pulls out the address in RAM that corresponds to that X coordinate. So basically, right, if we're looking at X position 0, so the first pixel, we're going to come to our RAM here, and we're going to look at the first value that's here, all the way at the top, and we're going to get a 0. And we're going to get this value of 0, this 8-bit value, and we're going to set our red color to the data that we get from the RAM. And this actually, it technically lags by one frame, so it's 1 pixel behind, but that's a technicality that we'll worry about later for now. And so in that fashion, it goes all the way across, and it keeps reading these values one by one, and the red color is equal to whatever, the level of red is equal to whatever this number is. Right, so we start at 0 again, we can work all the way up to higher and higher values until we get to 255, and then we go and roll over back down to 0. So, kind of fun. But yeah, so the other thing I can do here, if I wanted to, just to show you what I'm talking about. So let's say instead of using the X coordinate, we use the Y coordinate. So right now, those colors go from blue to red as you go left to right. But if you look up and down, right, up and down over here, the color is the same for every column. So if we switch this instead to run on the Y pixel to calculate our memory address value for our RAM, then we'll actually be left to right on the image will be the same color, but as you go down on the side, you'll see that the colors will go from blue to red, and then they will overflow past color 255 and go right back down to 0. And so we'll see a few steps of blue to red, then blue to red, then blue to red in that kind of gradient like we have right now, just in the opposite direction. So we're running our synthesis right now, just to show how that's going to look when we change this to be based on the Y coordinate instead of X. And while that's happening, obviously we actually want to start to store a lot of different types of data in RAM, right? Right now, for example, the actual image itself is hard-coded, the color palette is hard-coded, right? This is all data that we want to load from RAM instead. Even attributes on whether or not the sprite should be flipped, other sort of attributes like that, those also should be stored in RAM and read from RAM. It's a bit of a next step for us here. Probably a little challenging also, I think. But to start, I was thinking about just taking this data, and if I can read this data in for every pixel as we're about to draw that pixel, if we can read in what the image data is from RAM, well, then we'll have passed a huge milestone on being able to display data more dynamically, right? Because if we could do that, then at any given time we can actually start to have other processes that change the value of that memory, and we'll then start to show different pictures, and that's pretty exciting. I think it is. So to do that, really what we would end up doing is replacing our sprite data here with a call to fetch the data from memory instead. And something that I see as a challenge for that, well, several things, but one of the challenges is that our data for any one of these tiles, remember, is actually defined by 2 bytes. So to display accurately the type of data that we're showing right now with like Goombas and things, we would actually need to fetch multiple bytes of data, and that means we can't just load one byte of data at a time for every pixel. To do this well, we'll have to be a bit more clever than that, which is okay. I think we can do it, probably just not today. So first let me program the device and we'll see. Yep, there we go. Now the color, if you look from left to right, is the same, but if you look from top to bottom, it changes. Oh, also Mario's doing this weird thing where he's jumping around and he's moving slowly and weirdly. That's new. What's wrong, Mario? What happened? What did I do? Why are you so unhappy? I don't know why that is. Oh, that'll be interesting to try and look into. So before we can make things better, we're gonna have to break things a lot, because I want to see our ability to load data in, which we're doing over here, better. Okay. So let's say that we are looking at the x-coordinate. No, we're not. So the address should be set. We want to make sure we get the right byte. Right now we've been getting that byte by having this crazy multi-dimensional array and having it take care of some of the math that we have to do. And we'll have to implement the same kind of math that we had done before to make this work nicely. But right now I just want to read anything from RAM and I'll be kind of happy. So I just want it to change based on which X pixel and possibly Y pixel that we're looking at. Okay. Oh, did Mario disappear? Yep, Mario disappeared. Where'd he go? How'd he get lost? Some value must have exceeded some limit. He didn't bounce back from wherever he was supposed to bounce back from. Huh. We'll have to look at a recording later to figure out what just happened. We'll worry about him later. we're looking at background stuff right now, not sprites. All right, so so first of all, we'll just change this back. So we don't want to. We want to pick our colors based on our actual palette instead of our little hack right now, which is doing fun things with colors. But the address. So what address do we want to get per pixel? Take a second to think this through. So naturally, as we go further to the right, we'll get a later byte, and as we go down vertically, we'll also need to get a higher byte. And what's the logic for which byte we need to get? So if every image is defined, every kind of little tile that we have is defined as a as a 8 byte by 8 byte tile, 8 pixel by 8 pixel tile, each one consuming 16 bytes of data, then we want to take our x coordinate, right shifted in, because we basically want to tick to the right in a almost jerky fashion, right? For every tile over to the right, we want to then pick the next 16 bytes over. Okay. So if we right shift x by 3, then this value will only increment when x is increased by 8. That way we're saying, okay, we want the next tile over. Okay. And what we want to do is take that and go 16 bytes ahead for every time this increases by 1. So times 16 plus I actually don't know. If we go down a y, one tile down, how many tiles over is that? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So right now we have 20 pixels left to right. 20 tiles. So if every tile is represented by 16 bytes, right? And each one is 20 tiles over. Then when we go down one column, we'll want to go down by 320 bytes. So same logic, similar logic to the x. We want our y coordinate right shifted by 3. So every time this increments, we want to go the next column down. So that ticks up by 1. It's 320. This feels a little crazy, but maybe it'll work. Now remember, right now, the way that this is set up, our RAM data is pretty much garbage. So we will get a very weird, garbagey output. I think it will repeat in some fashion. But like all this stuff is going to be So that actually that does the address calculation. I still actually have to use the data, which is this thing in data. Okay. Yeah, our normal selected palette logic isn't gonna work right now. If, as written right now, it's literally just going to do exactly what it was doing before. We didn't change any functionality here, so we got to change this. Okay. Palette. And we're going to say it is the data from our RAM and we specifically need to get the X portion of it. Which is I think having a hard time remembering exactly how to do this. That's not going to be right. We need to pick the right, so we have 1 byte, 8 bits. Of the 8 bits from left to right, we need to pick the appropriate one based on the X coordinate of the byte that we're looking for, which is going to be here, this part. Sprite render X bitwise ANDed with 7, like this. And right now what we're missing is the other value. So let's go ahead and say that the selector palette is going to be 1 fixed value for the one of those bits, and the other value will be based on X. It will not look right, but it's better than nothing. Now, given that we know that this is going to generate garbage, it is hard to say for sure that we'll know exactly what we need to see. But we should be able to look at the first few pixels, knowing what's in our RAM up here. We should have a rough sense of, we should roughly know what we're looking for. And later we'll have to look into why Mario disappears. I feel like it's just hooked up to some weird value. The boundary conditions aren't being set correctly. Maybe the VSync signal isn't coming properly and isn't doing the right calculation. The thing is, I haven't done anything to the sprite, so I'm not totally sure. And yeah, for the clock for our RAM, theoretically we could run it faster, but I figure it's kind of fun to just run it on the same clock that we're using for all our graphics system, which is all based on the pixel. So later, if we need to load more data, either we can build a 2-byte, we can move to a 16-bit memory architecture, or we can load the appropriate bytes in advance, store it in a register, to kind of build our pipeline for doing all our graphics processing. That may be an exercise for, that's definitely an exercise for another time, but yeah, I'm not really sure yet exactly how to best read the data from the RAM when we're planning out our whole, our whole vertical line, and saying like, okay, how do we make sure we have the data we need when we need it, given that our RAM is running at the same speed as our pixel calculations. Right, one thing that's clear from this architecture is we need several bytes to do the right math, and if it takes one clock cycle to get 1 byte, then that means we need several clock cycles to get it all in place. And I think that's okay. We can actually handle that. We just need to figure out the best way to do it. Alright, so we'll go from something that I think looks pretty to just garbage. Let's see how bad it is. Okay. That actually seems like it could be what we need to see. So we have these lines. Also, Mario looks normal again. He's not doing anything too glitchy. Okay. Okay. Yeah, this is what I feared. Actually, very hard for me to figure out if this is what we need to see or not. Let's pull up our RAM. So we said that we were going to hard code. Let me shrink this guy down again. 1 second. Okay. So we said we were going to just hard code this, one bit of our palette to be 1, and the other one's going to be coming from the data in the RAM. That means our palette will be 1, 0 and 1, 1, which are these two colors. So not the darkest of blue for our Goombas, but rather the medium blue and the light blue, which are the ones that we're seeing, so that's good. So it's actually pulling out the, it is setting the colors that we would expect. Now let's just see if it's the right colors in the right place. So this is taking sprite render X and ands it with, hang on. So we're taking sprite render X and we're anding it with our value of 7. So basically every 8 pixels, it should reset. Now mind you, that's 8 pixels on sprite render X, which is already downsizing it by 2 bits, right? We already do this shift, so really what we're saying is it is those 8 pixels become 32. They become 4 times the size. So 32 pixels, and when it becomes 32 pixels, we are going to repeat. And that does look like it's repeating every 32 pixels to me. The first time it repeats seems a little soon. And I think that's because, again, we're actually accessing our RAM on a one clock cycle delay. But okay. And then let's look again. What are we seeing? So we see this like bluish color. And we see very thin lines when the color transition is occurring sometimes. And that's because our pixel clock, so right now we're drawing bigger pixels than our pixel clock, right? So again, we're multiplying everything by 4 to make it not only more fun, but honestly to make it less processing intensive. So it looks like when the color changes sometimes, right, it it takes a clock cycle, 1 pixel clock cycle for the RAM to give us an updated value, and we don't have the value in advance. So if we draw 4 pixels always on the same color, the thing is the RAM for the first pixel is giving us the wrong color. And I think that's what we're seeing here, both on the X and Y coordinates. And in the Y coordinate, what I mean is, if you look over here, hang on, there you go. So if you look over here, it's hard to see, but it's darker color here, but everything is downshifted a little bit. So you have a little bit of a light blue color over here in the first column, and the same thing on the top. That first pixel is darker, and then the rest become the right color again. So the implication to me is exactly that. So we're loading data, and we're not loading data in advance. Our pixel clock is the RAM just isn't ready. Basically, the data isn't ready. It's not loaded in a register, so things are just changing a little, all over the place. All right. So looking at the data again, what we're seeing here is, if you look at our bits in the RAM, our first view, it's all zeros, then there's a 0 and a 1, then all zeros again. So all of these should be because our first palette color is going to be static 1, the rest are all zeros, and so it's 1 0 1 0 1 0 1 0 1 0 1 0 1 0, and then it should be 1 0 1 0, and then we jump forward 16 bytes. Yeah, this works. So the next tile over, right, once we move past those 8, which are all zeros, right, so this is all should be the color 1 0, which is our lightest blue. Is that right? Yeah. Awesome. So I size this down a little bit. You guys can see. So the color 1 0 here is this one, which is the lightest shade of blue that we have. You can see from the hex values here, right? CE is higher than either of these. So this is the lightest shade of blue. And in fact, our first tile is colored in the lightest shade of blue up here. Our next tile, remember our logic, we don't just jump to the next byte. Instead, what we said was that our X coordinate, when you go to the next one, it should be up 16. So we should get byte number 16 from RAM. And if this was our first one, this is, I think this is the one that would be next. Yeah, because the RAM that we have here is 0 indexed. So, and this is indexed starting with 1 in our kind of lines on the text editor. So it should be 0 0 1 0 0 0 0. And what do we see? Something that looks nothing like that at all. This looks like 1 0 0 0 0 0 0 0. All right. Seems like something is wrong. So it still looks like it somehow is connected to the data that we have in our RAM. Right, this data. But it looks like it may be fetching a little bit the wrong data. But that's okay. Like I said, before we can make it better now, we had to make it much, much worse. So, congratulations. It is, in fact, much, much worse. But that's okay. This is, have to break a few eggs to make an omelet, that kind of thing. So that's pretty much where we are. And it's a good stopping point for now, and some good next steps, very clear from here. One is figure out how to load the right data in from RAM in a way that makes sense, in a way that's logically laid out memory. And then figure out why it's loading the wrong data. Oh well, we'll figure that out later.